In this lab, we will be analyzing a star as it orbits a black hole. Some of the physics principles behind this lab are curving motion, where the net force is equal to the sum of the parallel force and the perpendicular force relative to the motion. We will also be using this equation for the force of gravity, which is given using the gravity constant. And we will also be using Newton's second law, where the net force is equal to the change of momentum over the change in time. For the procedure for this lab, we are given the location of a star as it orbits a black hole at time t, where the time steps are days. We're also given the mass of the star, and we are trying to find the mass of the black hole using the position data. We can first find the change of position over time for each time step, and then from that we can find the change of velocity over time for each time step. Using the change in velocity, we can find change in momentum, and then we can plug in Newton's second law, where the net force is equal to the change in momentum over the change in time. And since we know the equation for the force of gravity, we can set F net equal to Fg, and then we can arrange this to solve for the mass of the black hole. And we can use the position data that was given to us to find the distance at each time step. Here's the Python code I used for this lab. At the top is a random seed generator, which gives me a seed for my position versus time of the star going around the black hole. Down here I inputted the gravitational constant, the mass of the star, and the time step in days. Right here is the while loop used to calculate the forces. The velocity final and velocity initial are used to calculate momentum final and momentum initial, and then we can find the change in momentum over the change of time, which is equal to the net force. And down here we can break up the net force into the parallel component right here and the perpendicular component, and the equations for this are listed right here. And further down we have arrows used to represent the net force, the parallel force, and the perpendicular force. I'm now going to run my code. The orange arrow represents the net force, the blue arrow represents the perpendicular force, and the purple arrow represents the parallel force. As you can see, as the star gets closer to the black hole, all of the arrows increase in length. This is to represent the force increasing. This is because the force of gravity is inversely related to the distance between two objects. Down here at the bottom, what's printing is the net force, the perpendicular force, the parallel force, and then the position vector. Using the equation for the mass of the black hole listed on the top, we can solve for the mass of the black hole at each time step. This is a graph of the calculated masses at each time step. Because we are using an iterative process, the data is not perfect and there will be slight deviations as shown here. However, the mass remains approximately close to each other. In conclusion, the mass of the black hole was approximately 8.8 times 10 to the 43rd kilograms. This in solar mass is 4.24 times 10 to the 13th, making it much larger than the Sun. If we were to change the unknown value for the mass of the black hole, we could still calculate it using the same method because the velocities would change and therefore the change in momentum over time would change. As for applications, this is very applicable because it is difficult to analyze black holes. We can analyze objects orbiting the black holes and then use this method to calculate the mass. This concludes my lab 3.